Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased selection. Today, actually, two theorems in one. And I just decided to, as I said, make them into one. So I'm going to explain the Kuratowski theorem and at the same time the Wagner theorem. And let's just call it the Kuratowski-Wagner theorem for a reason I'm going to explain later. So Kuratowski's theorem, one of the milestones of early graph theory, actually is in some sense before graph theory was even really a field of mathematics. So it's from the 1930s. Wagner theorem, one of the milestones of modern graph theory. Actually, before graph theory was really a field of modern mathematics, it's also from the 1930s. It goes back to two different people, Kuratowski, a Polish mathematician, Wagner, a German mathematician. And a lot of people kind of worked simultaneously on this, and those two names just stuck. So whatever, let's just go for Kuratowski-Wagner theorem. Kuratowski theorem, pretty famous. If you haven't seen it, you will see it in this video. Wagner theorem is kind of the same, and that's why I like to collect them into one theorem. So they're really kind of dual partners, if you want. And I call this the search for forbidden pieces. That's basically what it is. So forbidden pieces. So what could be forbidden pieces? Well, we'll see. But let's start with a puzzle. And this puzzle really originates before Kuratowski theorem. In some sense, Kuratowski theorem was a solution to that puzzle. But of course, you can find an easier solution, which I'm going to show you anyway. So you don't need to use Kuratowski theorem in order to solve this puzzle, but it's a motivation for the theorem itself. So the setup is actually pretty easy. You have three houses, a green one, let's say, a blue one, that's blue, a red one, and a blue one, and you want to connect them to, well, water, you want to connect them to gas, and you want to connect them to, and I'm using green for electricity just to make it easier to see, green electricity. So you want to connect those houses to those three, well, and house needs water, gas, and electricity, right? So you want to connect them. And by connect, I mean just draw a line, let's say something like that. And each house should go to each one of them, right? Each house should get water, gas, and electricity. So I can connect my greenhouse to those, I can connect my red house to those, and I can connect my blue house to those. Okay, that's what I want to do. And yeah, I just solved the puzzle. No, not really. So that was not really the puzzle. Maybe that was easy. That's what you want. But you want to do this in a way such that you don't have intersections. So this picture has zillions of intersections. And the puzzle is, can you do this without those connections between whatever water and house, gas and house, and electricity and house, without them to ever intersect? So on the right, so this was the setup, and on the right-hand side, you have a non-solution. So here, someone, link is in the description to the picture, tried a bit harder than my very naive approach to just to just connect everything using a straight line, and it still doesn't work. So here, this, whatever it is, orange edge intersects the blue edge, and yeah, there's just no way to make it work. And it was already a bit fancier. As you can see, they are not using straight lines, but they're using those curved lines, and they try to go around and everything. So yeah, so if you try around a little bit, you probably will convince yourself very quickly, and I'm spoiling now the answer, that you can't. And there's a very slick way of proving that. So you can't solve, well, you can't connect them without ever crossing lines. So this is kind of always the optimal solution. You can connect them by crossing once, but you can't connect them by crossing 0 times. And here's the proof, which I stole from the same website, linked in the description, of course. And it's secretly, well, it's a proof without words. So actually, I should start waffling. I should stop waffling because it should be a proof without words, right? But it took me a while to understand the proof. So let me at least explain what's going on, why this actually is proof that, or kind of part of a proof that this is really impossible. Well, the point is, I kind of ignore my house here, which was the green one on the other slide. So I should make it green. So it was the green one on the other slide. And just solve the puzzle for 2 houses and those still water, gas, and electricity. And that's not hard. As you can see, here's the solution. And what you need to convince yourself is whatever kind of solution exists for 2 houses, you will always have something that is stuck. So here my little green bubble, which is basically not visible, so let me make it black. So here my little black bubble, electricity is stuck in the sense that no matter what I do, it's bounding the blue region and the pink region, but it needs to go into the yellow region. And there's just no way to do that without crossing ever the lines, right? That's the whole point. So I can go into the pink region, I can go into the blue region, but because everything is now divided into regions, I know no matter what I do, I need to kind of cross this line. And I know no matter what I do, I need to cross this line in order to go to my house, because my house is in the yellow region. And that's a proof that this problem can't be solved. Well, that was the puzzle, and the answer to the puzzle is no. Okay, so we just solved the puzzle. So what? Turns out that this is actually a beginning of a very important milestone, as I said, in graph theory. So let's have a look at a more formal description. So my house problem from before can be formulated in terms of this graph. So it's called K33, and it's a complete graph on the complete bipartite graph on 6 vertices. And what does this mean? Well, it means I have 2 groups. So that's why it's called bipartite. Well, let's say a pink group and let's say a green group on the other side. And they are kind of 2 sides, bipartite, right? Left and right side. And complete, this funny word here that you will also see here in a second, means now this vertex is connected. So this one here is connected to all the others on the other side, right? That's what I did. So those are the houses. Those are my little houses here. And those were whatever, gas, electricity, and water, for example. And you want to connect everything from the left to everything from the right. And as you can see, that's exactly this graph. So my problem from before can be reformulated in the following way. It's a question whether this graph K33 is planar. What does this mean? Well, a graph a priori is an abstract object. It consists of a collection of vertices and a collection of edges. This thing is a collection of vertices, the collection of edges. So the edges are obvious, there's the connections, and the vertices are kind of also obvious, they are just given different symbols. This is just a strapped down version of it. But it's an abstract object, it lives nowhere, it's abstract. But every time you draw a graph, you actually kind of want to embed it into the plane. You want to draw it in the plane because that's how I can draw things. I can't really draw things in 3 space or in higher spaces. So I like to draw them on the plane. And while doing that, I kind of chose an embedding of the graph into the plane. Not quite. I chose an immersion, and an immersion just means edges can intersect, like in those 2 pictures. An embedding would be if edges won't intersect. So here would be an embedding of a graph, which is actually kind of a triangle graph. Right? It has 3 vertices, 3 edges, and yeah. So this is embedded. Those things are not embedded. And now you have the following question: you have an abstract graph. It's given by an abstract datum. And can you actually find an embedding in the plane? That is, can you draw it without ever lines intersecting? And yeah, that's exactly this question, right? Can we draw this graph? The graph is a connection between water, gas, and electricity in my 3 houses without ever intersecting. In this case, the answer is no, and it wasn't quite obvious. Otherwise, this would be a very boring puzzle. Reformulated would be this abstract graph K33 is it planar or not? The answer is no, it isn't. Here's another puzzle. Here I have drawn a graph. It's called the complete graph on 5 vertices, usually denoted by K5. That's exactly the same idea. It's complete, meaning that every vertex you see is connected to any other vertex you see. Number 5 just means you have 5 of them, and now there's no condition onto left and right, so it's just 5 vertices, and each one, let's say the top one, is connected to all the others, as you can see. And again, you would ask the same question: can you embed this into a plane or not? I mean, I've just chosen one drawing. That doesn't mean there is no other nicer drawing such that is actually embeddable in the plane. Who knows? Kind of fun exercise for K5, it's not so hard to show that it's also not planar. You cannot find a drawing such that this one actually lives without intersections in the plane. And then this was kind of a problem you would like to solve, a very simple question in graph theory. So given this abstract, this or any abstract graph, so those two or any abstract graph, can you actually somehow decide whether it's planar or not? I mean, here I needed kind of an argument to show that it's not planar. Also, the argument in the end wasn't all that bad. If you imagine now a really big graph, I mean, that might be really tough, right? Who knows? Best would be you would have some kind of algorithm that can decide whatever is going on. And as a kind of such an algorithm is provided by the Kuratowski-Wagner theorem. So the Kuratowski-Wagner theorem gives you a criterion whether a graph is planar or not. And I will zoom on into this in a second, but let me just state the theorems here. So Kuratowski at the top and Wagner at the bottom, and they're really the same. One of them is a bottom to top, I call it a bottom to top approach, and I call the other one a top to bottom approach in the following sense. They are both stating kind of the same thing. A graph is planar if and only if something happens. And the bottom to top approach is if and only if it doesn't contain a subgraph, which is a subdivision of, well, my two funny things here, the forbidden pieces, the K5 and the K33, right? So forbidden pieces, K5 and K33. Dually, that's why I would like to collect them in one theorem, a graph is planar if and only if it does not contain K33 or K5 as a minor. And yeah, let's zoom into this problem and let me explain what actually the difference is. It's kind of really the same statement, up to that you go either from bottom to top. So you pick something and you make it bigger, or you start from the top and you make it smaller and look for K3 and K33 or K5. A point about those two theorems is, of course, first of all, they're both if and only if theorems, which is always good. And second, they have kind of the same type of forbidden pieces. That's the only thing you ever need to look for. So in some sense, to make this decision problem, whether a graph is planar or not, you only kind of need to prove it for K33 and K5 and then apply those, either of those theorems, whatever is easier. I will show you an explicit example in a second. But let's understand those two notions of a subdivision and a minor. So a subdivision is you start with a small graph, let's say G or G prime. So many subdivisions could lead to the same big graph, we call it H. And it's really just a silly procedure. You just take an edge and you put another vertex on that edge. You just take an edge and you put another vertex on that edge. So here I should have put 4 vertices, and you can repeat that, right? So the graph H in the middle is a subdivision. You subdivide an edge of the other two graphs. And then the statement is, you start with either K33 or K5. That's how I want to think about it. You subdivide it in some crazy way. You obtain some other graph, and that other graph is a subgraph of the graph you started with. It's a bottom to top approach. In contrast, or whatever, dually, there is this notion of a minor, and the minor is top to bottom approach. So in some sense. So now you would start with your graph and you would look for a minor, which is K33 or K5. So what is a minor? So this thing here is a minor of the graph on the right-hand side. And it's a minor in exactly the sense that the green vertices are the vertices of the, so let me call this G and let me call this H. Again, the big one is H. So G is a minor of H, and the vertices that I've marked in green exactly the vertices on the right-hand side in H, and the edges that are not dashed are exactly the edges on the other side. So the two allowed operations here to go from H to G are erase edges, erase vertices. So I erase this edge, this edge, this edge, and I ignore this vertex. Okay, and then you're almost there. Then the next operation you can do is you can contract. So kind of the undo of the opposite operation correspond to subdivision. If you have two neighboring vertices, just stick them together to be one. Okay, and then you have those two very nice theorems, which give you an if and only if criterion, reducing it to two forbidden pieces, which is pretty amazing if you think about very complicated graphs in this setup. Okay, yeah, so let me show you an example. So having those statements, those theorems is pretty good. So for example, Mathematica, I link in the description, has a function and algorithm to decide whether a graph is planar or not, which I think is pretty amazing if you think of, as I said, think of a big graph. But let's have a look at the not too big graph, namely one on 10 vertices, called so-called Peterson graph, the kind of standard example in graph theory ever, always. It's just a pentagon. So, and then you have another pentagon inside, which I shouldn't draw as a pentagon. Then you have another pentagon inside, but it's the pentagon inside is connected as a star. Oops, whatever. And then on the outside, it's connected to the pentagon. So it's really just this whole beast here. This whole beast is the K5. Sorry, is the Peterson graph. And this one contains K33 on the right as a subdivision. I will show you an animation in a second. So it's not planar. So you don't even need to think anymore whether this is planar. In mind, this is just one drawing, remember. It could be some other crazy drawing, which makes it planar. Nope, it can't, because you just have identified K33 as a subdivision subgraph. So there's a subgraph, and the subgraph has K33 as a subdivision. It's a subdivision of K33. On the left-hand side, the dual statement, it contains K5 as a minor. And how do you see that? So I don't even need an animation. This is a little bit easier. You just take the pairs of vertices, the natural pairs, and you just contract them to be one. And if you do that, so you just contract all those 5, you get exactly the K5 graph. So again, it's not planar. You don't even need to think about it. The other process is a bit more complicated. So let's have a look. It's actually not much more complicated. So here's the animation. We will run through it a few times, but you can already see what's happening. So I stole this animation, of course, from a website. It's linked in the description. But anyway, so let's have a look. So the starting point is our Peterson graph. And now you take a subgraph, so you erase that vertex, and now you do this this merging procedure, which is just the undoing of the subdivision. And there you go. There's your K33. So let's have a look for a second time. So first, take out the subgraph, undo the subdivision. Another one, and you're done. So here's your graph, K33. So it's not planar. Very good. So let me wrap up. So I stole the idea for this video actually from a very nice website, which has both Kuratowski's and Wagner theorem in 2 different theorems. It's called, the website is called Theorem of the Day. And basically what they do is they have 1 theorem per day, or which fits in the description on 1 PDF, so on 1 PDF page. And it's very nice, linked in the description. And as I said, they had Kuratowski's and Wagner theorem as separate theorems, but I kind of want to see them as being one. They're kind of exactly the same kind of type of statement. One of them is bottom to top and one of them is top to bottom. Okay, fair enough. Which one you call bottom to top and top to bottom is a bit of a matter of taste. But anyway, one of them is, in my opinion at least, saying you have those 2 forbidden pieces, K33 and K5, and you either build it up from there by subdivision, that's Kuratowski, or you have your graph and you look by taking minors for, again, the forbidden pieces K33 and K5. And so this Kuratowski-Wagner theorem gives you a very efficient, well, maybe not very efficient, but at least an effective theorem, and if and only if theorem, to decide whether a graph is planar or not, which is absolutely not trivial at all, right? Remember the puzzle at the beginning, which was just a really, really tiny puzzle. Now try to apply, well, ask the same puzzle for a much bigger graph. Anyway, I'm already starting waffling again, so I hope you enjoyed the video, and I also hope to see you next time.